Hello, and thanks for coming back. Um, in this video, I want to study energy transfer rates. So the energy transfer rate is what it sounds like. It's the rate of change that energy can be transferred, and we can be referring to all the types of energy, and we mean per unit time here. So it's really pretty simple. Um, Before, we had various ways to write the first law. One of them was the differential form, which stated that d the kinetic energy plus dpe plus du, the specific, or sorry, the internal energy, equaled a little bit of heat. And because that's an inexact quantity, we put a q there, or a delta, minus delta W. All right, so these are baby changes in energy, and we want to talk about a rate of change with respect to time t. And so this equation is going to become dke dt plus d potential energy dt plus du dt, the rate of change that the internal energy changes, and that must equal. So I could write it like this. In fact, I write it that way a lot. However, your book likes to write this. So this is how I think of it a lot. But your book will frequently use a dot notation for derivatives. And so it actually, for whatever reason, likes to do it like this. dke dt plus dpe dt plus du dt equals, and they'll write q dot minus w dot. These all mean the same thing. It's just for whatever reason they like to write this. Now, these kind of mean what they look like. This is the rate of change of kinetic energy, potential energy, internal energy. This is called the, actually, let me draw it over to the side. This is called the heat transfer rate. This is the rate of change. Is basically how efficiently heat is added or taken out of the system. And W dot, sometimes we call this energy, like they'll call it like the transferred work, but they also a lot of times call this the power delivered, if positive, or power consumed, if negative. Okay, so in terms of like a car, the power delivered by the car engine that would be W dot, and you'd measure that in horsepower or some equivalent unit. Okay, so those are It's more or less an obvious thing. It's just including rates of change with respect to time. And what that allows you to do is to talk about, well, a lot of times this is a more relevant expression. Um, for example, think about a light bulb. Do you really care how many kilojoules of heat it's radiated away since the moment it was plugged in? No, nobody cares about that. What we care about instead are the amount of kilojoules consumed or delivered in each instant. So what's the rate of change of heat is what we really care about in that situation. Okay. Now, we'll have more to say about some of these other ones. I do want to kind of focus here on the heat transfer rate. So I should say, basically, oh, I apologize, my stylus is kind of going crazy there. Basically, we will be looking at, when we use that equation, we will be looking at steady state. And what that will mean is all of the properties are constant. So one way you could think of this is you're adding water into a pipe, but you're also taking water out, and you're adding it steadily and you're taking it out steadily. And so inside the pipe, the water always enters the same and always leaves the same. And so none of the actual features are time dependent. Now, that's not how machines run all the time. So even though this is what we will talk about this semester almost exclusively, when you turn on a machine, it has to start from rest. And so there's going to be all sorts of transient startup sorts of phases where maybe at first the pressure spikes high, then it settles low, and then maybe oscillates, and then hopefully comes into equilibrium. So there can be transient time dependence. Now, if some of you guys are going to study heat transfer, especially if you're studying mechanical engineering or something like that. So we're just going to very, very, very quickly state the most important modes of heat transfer. So here's what we have. We have conduction. So modes of heat transfer. We can have conduction. So this is kind of like when neighboring molecules bounce into each other and they just sort of, if your neighbor starts shaking around a lot, then pretty soon you're going to start shaking too. And so it's kind of like a fire brigade where the energy is just handed molecule by molecule by molecule, like firefighters passing buckets down a chain. And eventually everybody starts moving and heat is transferred. So the equation for that would be Q dot and your book puts an X there. So I'm going to do that too. But really, that's just to indicate conduction. And I suppose it actually might be a Greek letter chi, but the typeset's too small. Oh, no, I'm sorry. I'm misunderstanding. The X just refers in 1D. So this is 1D. You can have conduction in multiple dimensions. So it'd be the X direction here. And it's equal to minus a constant called kappa. or well, this Greek letter is kappa. It's called the thermal conductivity, times the area. More area means more contact, so you get more conduction, times the rate of change of temperature with respect to position. So what that means is, let's imagine we have a house, okay? And inside the house in wintertime, so inside we have, let's do Fahrenheit. So say in the inside it's 70 degrees Fahrenheit, and on the outside it's 20 degrees Fahrenheit. And so the idea would be, and we could assume maybe that it linearly interpolates between there. So you might say, okay, the temperature, assume that the temperature in the middle is like, some sort of a slope, delta t over delta x, where x is the perpendicular direction. That's a constant slope times x. So you get a graph for temperature, which in that case, which would be like this as a function of position. It would be like 20, 20, 20, 20, 20. Oh, sorry, my stylus is getting wonky on me. And then it would linearly increase and then become a constant again. And so this would be at 20, and this would be at 70. Okay, so this would be a situation where you would have a linearly increasing temperature in the middle, and so you get a slope here, which would just be the slope of this curve, temperature versus position, and there would be some coefficient called so kappa is called the thermal conductivity. So if kappa is large, it's going to be easy to transfer heat. And if kappa is small, it's going to be very, very slow. It's going to be hard to transfer heat with this mechanism. All right. There'll be some homework questions on this. All right. Another mechanism for heat transfer is called radiation. Now, people have all sorts of nuclear, energy ideas or nuclear radiation. But what happens in radiation is really that the mechanism that the energy is transferred travels much faster than the motions of the atoms themselves. And so basically the energy is just kind of carried away and leaves the body. So it could be light, but it could also be subatomic particles. It could be lots of things. All right. So radiation follows the so-called Stefan Boltzmann's law. And that says that Q dot, so the rate of change or the heat transfer rate using radiation, and here we're putting E for this type, and it equals epsilon times a constant called sigma, it's called the Stefan Boltzmann constant. Right? I'm not going to derive it, but well, there's a whole long history behind that. The area, bigger area, radiates more, times the temperature to the fourth. And that's very famous. Temperature to the fourth is famous for the Stefan Boltzmann law. So how do you think about this? Well, think about if something's really hot, it radiates more heat. So if it has a high temperature, you know that the heat transfer rate is large. If something is huge, we also know that the energy delivered is large. So You could have a giant cold fire, so it's like a red fire, versus a really teeny tiny blue fire. Well, we know that if the area is large enough, the giant fire will emit more heat. Epsilon, so sigma is the Stefan, Boltzmann constant. It has a numerical value, and just look, if we need it, I can't remember if we need it this semester, but if we do, it's just in the book. Or it has a numerical value. Drawing a blank off the top of my head. And then epsilon is called the emissivity. And basically just it's kind of like a fudge factor. What happens is and epsilon ranges from 0 to 1. So it could be equal to. If it's 1, then we call such an object a black body. Right? And that's a famous kind of idealized object that people imagined. And understanding that leads to really it leads to the birth of quantum mechanics, and so that's why there's a whole long history behind studying such things. And emissivity is really kind of like a fudge factor to go from an ideal kind of configuration. When epsilon is 1, it's sort of a theoretical extreme that can't really be realized, and then epsilon is just kind of like a fudge factor to account for reality, in essence, the fact that things aren't perfect. Okay. We also have convection. So convection is, well, you might be familiar with it in a stove. So this is where, so think about what happens in a stove. It's just a fancy way to say you turned on a fan. The idea with convection is that you are kind of moving kind of bubbles of fluid with same temp. Okay, so the idea is you'd have like a bubble of fluid, and the bubbles like a bubble of hot air or something, and it would move together. It doesn't have to actually be a physical bubble, but it's just a little region, a hot pocket in the fluid. So the law to understand this is it's called Newton's law of cooling. And that it's sort of similar to conduction, except we don't have a derivative. With Newton's law of cooling, it's actually just a difference in temperatures. So we would say Q dot, and your book puts a C there for convection, and it equals H, a constant, times the area times the difference in temperature. So it'd be temperature, well, we'll talk about this, but it'd be hot minus T cold. Okay, I'm going to make a comment about minus signs here. And H is called heat transfer coefficient. Common numerical values. Basically, the difference is it forced air or is it just kind of stagnant? So if you force the air, like with a fan, the transfer is much greater. So basically, like according to the book here, typical values for a gas or liquid for H. And this is for, they call it free convection. Is something like, they say 2 to 25, and the units on that would be watt per meter squared times Kelvin. Or in other units, if I measure it in BTUs per hour. BTU is an energy unit, so I have to do BTUs per hour to get a power. And then I need a feet squared, because I have an area. And then I need a temperature, and they're going to use, instead of Kelvin, they're going to use Rankine. So I'll put degree Rankine. Okay, and that would be, in these units, 0.35 to 4.4. Okay. All right, for liquids, these same numbers are like 50 to 1,000. And over here in these units, I have like 8.8 to 180. All right, so that's when you just let it kind of gently float and rise. If you turn on a fan, like in a convection oven, so this we call this forced convection, what you see is that that it's going to increase. So these same numbers would become 25 to 250, 50 to 20,000, 4.4 to 44 in these units, or 8.8 to 3,500. Okay, so the idea is with convection, you get a much faster heat transfer if you turn on the fan. Okay. All right. Now, a comment about minus signs. People always get hung up on this because you're right. We have a formula here with Q dot, and then over down here I say Q dot equals this, and then or Q dot equals that. And this, incidentally, this radiation could be the formula for the light that leaves the object, and also it can be the formula for the light, or it's not light, for the radiation or heat absorbed. It has the same formula. And then over here I have a different one. Here's the thing. As far as the minus signs go, the heat is going to flow from hot to cold. So when you're talking about a heat transfer rate, you need to talk about and think about the direction of flow that you're talking about. And you just use that, the fact that we say the heat flows from hot to cold, to figure out the minus signs. That's much easier than trying to just memorize, I don't know, all the special cases. Just think about it. Just think it through in each problem. If you get it wrong, you're going to get a fireplace cooling off the room instead of heating it up. So it should be obvious if you get it backwards. Okay. All right. That's what I wanted to talk about here in this video, where I talked about heat transfer rates or energy transfer rates, and then forms of heat transfer. We will have a few simple examples of this, just so you kind of know how it works with heat transfer rates, Q dot. Almost always in this class, we will work in steady state, And we'll just say that Q dot is just some fixed number. When we go to build a power plant or design an engine or something. Anyway, maybe not for a car engine, but for at least for like a power plant, when it's in the boiler, when water's in the boiler, we'll just assume the heat transfer rate is some constant value. So we won't spend lots of time with these more complicated formulas. They each have their own regime of validity and utility, and you'll deal with those in more advanced courses. All right, thanks for watching. I'll catch you next time.